much for the oh, there we go. Thanks very much, Craig. I appreciate the kind introduction, and also appreciate everybody who's tuning in. Yeah, I'm really excited to give this talk. This is something of a departure for me. I usually don't think about these kinds of processes and these kinds of short timescales. As I was telling Klaus earlier, I usually live in mean sea level world, thinking about monthly and longer periods and much larger spatial scales out in the open ocean. So again, this is something of a departure for me that was really, really fun. I say that partly because I'm going to plead ignorance here. Again, I don't pretend to be a hydrometeorologist or a hydroclimatologist. So you'll find that my knowledge of the atmospheric river phenomenon is actually pretty limited. My perspective here is that I'm interested in the ocean's response, particularly as manifested in sea level. And for me, the atmospheric river process is taken as a given. It's the surface boundary conditions that drive an ocean response. So I say that to not be surprised if you come up against the limitations of my understanding of the phenomenology of atmospheric rivers themselves. I'm focused more on understanding how the ocean responds to those phenomena that have been discussed in depth by previous authors. So I'd like to acknowledge my co-authors who were instrumental in helping me put together a coherent manuscript here, and this is all funded by the NASA Sea Level Change team. To misquote T.S. Eliot, in my beginning is my end. I will start with my conclusions so that if you need to leave for lunch or you lose my train of thought or whatever else, you'll at least get the main point. So key points are as follows. High tide floods on the US West Coast co-occur more often with landfalling atmospheric rivers than you'd expect from chance. Okay, some vocabulary words in that sentence that I haven't defined yet. I will in a moment, so don't worry if we don't understand what all those phrases mean. More quantitatively, depending on where you are along the West Coast, we're talking a southern boundary down in Southern California around San Diego, all the way up to the north to the Puget Sound in Washington. Depending on where you are along the coastline, between about 10 and 60% of the high tide floods that are observed by tide gauge records in the past 4 decades coincide with landfalling atmospheric river, again, depending on your location. If we're interested in the physics of the storm surge associated with atmospheric rivers, we find that it's really alongshore winds, which are oriented north-south, alongshore winds and barometric pressure that are the main drivers of the storm surge during these events. But interestingly, something that doesn't get as much attention, we believe that rainfall, so the precipitation associated with atmospheric rivers, is actually strong enough that it affects a dynamic ocean response that's manifested in storm surge as well. Again, if my talk gets you interested in this topic, there's much more detail in the paper. So this was published in GRL just a couple of months ago. It's open access, so should have no trouble getting the paper. And we'd love to know any thoughts you have. So feel free to follow with me afterwards if you have any questions or comments on the manuscript itself. So with that, I'll start the talk. So let's start defining some terms. So first, atmospheric rivers. Atmospheric rivers are very long, narrow, filamentous features in the lower atmosphere. They're very moisture laden. They transport a lot of water vapor, and they're typically associated with the cold fronts of extratropical cyclones. So I've got a map here of the Pacific Ocean. I've drawn an orange box, which I'm using to kind of highlight one of these filamentous atmospheric river features. So what I want you to focus on is this long feature that stretches kind of sinuously from this bottom left of the box to the top right, where it sort of makes landfall with the US West Coast. This is one of these atmospheric river features, as evidenced in, look at the chat here. Oh, thank you, Klaus. This is one of those atmospheric river features making landfall on the US West Coast. These features are really important for a couple of different reasons. One is that they're huge players in the global hydrological cycle. Even though they're really ephemeral, transient phenomena, they're responsible for a lot of the mid-latitude poleward transport of water vapor in the atmosphere. So they're certainly important from a hydroclimatological point of view. They're also probably more well-known because of the impacts they have on human beings. Again, as their name implies, these features, these atmospheric rivers, are associated with, once they make landfall and they experience, say, orographic lift along the US West Coast, all that moisture rains out. You get torrential rains very strong winds, and a whole host of impacts on human beings. Here are some example photographs. These are all from NPR reporting on particular atmospheric river events this past fall. So October, November, December 2021, primarily in Oregon and Washington. And we can see all the expected impacts here. We have inland flooding. We have really strong winds that also go with these events that you can see manifested in this downed tree on the left and the downed power lines. Really dramatic mudslides and rock slides. People we're getting familiar with seeing images like this. When I started thinking about these impacts as someone who's interested in sea level, and I thought, okay, these atmospheric river events are associated with strong precipitation, strong winds, presumably low barometric pressures. For me, I think, oh, well, that's sort of a recipe for storm surge. Is there coastal flooding that's also experienced during these events? And surprisingly, I found that even though you have pictures like this gentleman here along the coast in Oregon during one of these events, sort of taking in the waves, not much has been written about the coastal impacts of these events, which I was particularly surprised by. So there's two concepts that I'm interested in probing here, insofar as they relate to atmospheric rivers. One may be more familiar than the other. So the first concept, just to define my terms, is storm surge. Again, many in the room may be familiar with this. By storm surge, I mean an unusually high sea level, so still water level above the predicted tide, usually associated with the intense meteorological conditions associated with a storm, hence the name storm surge. High tide flood is something that's maybe less familiar to people, and we're going to give it a precise name here. So a high tide flood, by high tide flood, I mean a coastal flood that occurs when the still water level, still water level is the physical quantity measured by a tide gauge. It comprises mean sea level, the tides, and storm surge. When this still water level exceeds some local minor flooding threshold, a flood stage that corresponds to impacts like inundated roads or sort of water bubbling up through storm drains, these kinds of events negatively impact transportation, property, public health, and safety. They also go by other names. You may have heard them called nuisance floods, sunny day floods, recurrent tidal floods, pick your poison here. The name high tide flood is not meant to connote that these floods are due to tides only. They're not tide only floods. The name high tide flood, in my understanding, is meant to denote the fact that whatever the driver is of the flood, its impacts are felt most acutely at high tide. Okay, so I'm interested in understanding these two phenomena during atmospheric rivers. So going to the literature, I found, like I said, that not much had really been written about this topic. So there's only a couple papers that look at the relationship between atmospheric rivers and coastal floods. The first one is this paper about 5 or 6 years ago by Piecuch and Villarini. They're looking at the West Coast. So here are some maps showing results from that paper. Each dot along the coast is the location of a long tide gauge record. And these authors interrogate the question, what's the relationship between landfalling atmospheric rivers and extreme sea level statistics? So they couch their study in the language of extreme value analysis. They look at typical extreme quantities like block extremes and peaks over threshold. So they look at, for example, the top two plots. This AMSL quantity is the annual maximum sea level measured in an hourly tide gauge record. So that's their block extreme. And then peaks over threshold, they essentially count in a tide gauge record how many times the water level overtops, I believe it's the 99.7th percentile of the empirical water level distribution. So they use these two measures, the event time of the annual maximum and the event time of peaks over threshold. And they simply ask, how often do those events coincide with the landfalling atmospheric river? And depending on which quantity you pick, whether annual maximum, peaks over threshold, and depending on which location you're at, you can find that up to 65% of the time, that extreme value statistic can coincide with an atmospheric river. So they do find a strong relationship between these quantities. Here's the catch. This is informative. When I approached this topic, I was primarily interested in concrete impacts, things that affect people and property. And it's really not trivial to go from the result of this study, which look at extreme value statistics, and something like a high tide flood, which is defined in terms of impacts. For example, if you have a year where no high tide floods happen, then the annual maximum sea level you identify is not going to correspond to a flood. So you can interrogate that event but it's not, it doesn't correspond to anything in the real world that impacted people negatively. Vice versa, if you have a year where you have multiple floods, if you're only looking at the annual maximum, then you're missing a bunch of floods. You can make similar considerations with respect to the peaks over threshold statistic. If the peak they pick is actually much lower than impact-based thresholds. So again, helpful paper, moves the needle forward, but we really don't have a sense of the impacts along the coast related to these events. A subsequent paper by Shinoda et al. So these are reporting results from the Cal Water 2015 campaign. This is an observational campaign in the early months of 2015 to understand the impacts related to atmospheric rivers. And I'm showing some of the results here. So the two maps, again, we're on the West Coast. The color shading here is the total column water vapor in millimeters of H2O equivalent. And you can see two atmospheric rivers as these bright red sort of narrow bands that are making landfall along the coast. The two colored dots, the blue and the pink, those are two tide gauges, one at Mia Bay in Washington to the north and one in South Beach, Oregon to the south. They're looking at the storm surge associated with these events. So two events, one in mid-January, one in early February, left and right. If we look to the bottom left of this plot, the time series, so these are sea level tide gauge data. So these are daily averaged water level from the two tide gauges I just mentioned. And if you look, there are two very prominent peaks here, one in mid-January and one in mid-February, early February. These are storm surges associated with the landfall of these atmospheric rivers. So we see the evidence of storm surge in these tide gauge records, and these authors use a model. They use the high resolution HICOM model. So this is data assimilating 1/12 of a degree to simulate these storm surge events. And it's the model output that's shown on the right in panel D. So again, the colors correspond to different sites. You're showing sea level in both panels. And we can see if we sort of toggle our eyes back and forth between panel C and D that the model does simulate strong storm surges during this January 16th and February 6th event, but don't be fooled here. Look closely at the y-axis limits of panel C and D. Panel C's y-axis limit is twice as high as panel D's. In other words, HICOM is simulating the timing of these events, but only about half their magnitude. Now, this is interesting. So Shinoda et al. Speculate that the reason you get this mismatch between the observations and the model with respect to the magnitude of storm surge is because HICOM, which again is 1/12 of a degree, isn't sufficiently high resolution. That there are all these really small scale local processes that are important for understanding the storm surge. That's a really interesting hypothesis because it kind of goes directly against other hypotheses for what the dominant drivers of storm surge are along the West Coast. For example, this paper in 2017 by Bromerski et al. They hypothesized that the main driver of storm surge along the coast is actually the ocean's isostatic response to barometric pressure, the so-called inverted barometer effect. Interestingly, models usually don't include atmospheric pressure as a boundary condition, so the IB effect wouldn't be simulated by HICOM. So we have these two apparently different hypotheses, one from Shinoda that very small scale physics is important for generating the storm surge, and the other implied by the Bromerski study and others that what's missing in the model is the inverted barometer effect. So we have so what's the point? The point is that we have open questions as to what the dominant drivers of storm surge during an atmospheric river are. So those are my two questions. Again, here's our vocabulary terms again, but the arrows on the bottom state my question. First, what is the relationship between atmospheric rivers and high tide floods on the West Coast? And second, what are the meteorological factors that cause storm surge during atmospheric rivers? So in what follows, there's going to be three sections. I'm mostly going to focus on the first two, which are largely statistical in nature. Depending on time and the room's interest, I may get a little bit into physics, but probably won't get too into the weeds. So that's the structure. So what's my data? So of course, if I'm looking at coastal sea level, I'm going to use tide gauge records. So I use hourly still water level. So again, still water level being the sum of mean, tide, and storm surge. So we're filtering out all the waves, essentially. Using hourly still water level data, tidal predictions, and also station datums for 24 tide gauges along the West Coast, as shown by colored dots in the map on the right. So these are from NOAA co-ops. Okay, the reason I choose these is because they're long records. They span a couple decades. They're mostly complete. They give good geographic coverage. There's no really big gaps along the West Coast, geographically speaking. And finally, this is kind of a practical decision. These are the same sites that are used in previous studies of high tide floods, or excuse me, of atmospheric rivers in government reports on high tide flooding. So we're able to provide results that are interpretable in light of past findings. So main data set here is the tide gauges, again, hourly resolution. If I'm studying atmospheric rivers, I also need an atmospheric river data set. So the one that I used here is the Scripps Institution of Oceanography AR catalog due to Gershinoff et al. So this is a derived product. What this amounts to is the authors here have taken the NCEP-NCAR reanalysis 1, and they have designed an automated atmospheric river detection algorithm that they apply to the reanalysis. Okay, so what they do is they have this algorithm that essentially cycles through every 6 hourly time step of the reanalysis, and it interrogates every grid cell to see whether certain criteria are satisfied. I've listed them here. They relate to whether a feature has a specific spatial extent, temporal duration, and particular features of its integrated water vapor and water vapor transport. So if these criteria are satisfied, if you're very long, if you last more than 18 hours, if you're transporting this sort of minimal floor of 250 kilograms per meter second of water, and you've got at least 1.5 centimeters of water in the column, that is called, according to these authors, an atmospheric river. So once they identify these features, they identify the landfalling location, which is the grid cell in the reanalysis. So the boxes on the right are the reanalysis grid cells, pretty coarse. The landfalling location is the coastal grid cell with the maximum integrated water vapor transport. So this is their algorithm. There do exist other other AR detection algorithms, which I can talk about later, but this is the one that our study is based on. For interpretation purposes, I also use daily winds, air pressure, and rainfall from that same reanalysis. But in the results I'm going to show related to interpretation in a couple slides, I've also done this with other reanalyses, and you get very, very similar results. So the results aren't super sensitive to the choice of reanalysis there. That's what that asterisk is reminding me to say. Here's our data. We consider them over the overlapping period between 1980 and 2016. For those who study atmospheric rivers in the room, this almost perfectly corresponds to the period of ARTMIP, the Atmospheric River Tracking Method Intercomparison Project. So it can be interpreted in light of ARTMIP results. So first question, what's the relationship between high tide floods and atmospheric rivers? This is a very, very simple exercise, okay? We're going to try to establish the relationship between these two phenomena, ARs and high tide floods along the West Coast using a peaks over threshold similar to Kawaki and Villarini, but with a distinction. Remember, Kawaki and Villarini counted peaks over threshold using an empirical percentile of the water level distribution. We're going to use, instead of that, we're going to use these impact-based thresholds. So I'm going to count the number of days in each tide gauge record when a high tide flood occurred for at least 1 hour. I'm called that a high tide flood day. What do I mean by a high tide flood occurring? I mean that a high tide flood occurs when the still water level exceeds that minor flood threshold due to Billy Sweet and colleagues. Just for reference, this tends to be about 55 to 65 centimeters above mean high tide. So I count the number of high tide flood days. I also count the number of days when an atmospheric river passes nearby a tide gauge. I call that an atmospheric river day. What do I mean by nearby? I mean, my definition of nearby here, that an atmospheric river is nearby a tide gauge when it has integrated vapor transport above 500 kilograms per meter per second. So I impose sort of a higher floor on the IVT magnitude. So we sort of filter out more sort of weaker, more beneficial events. So it's got to meet that IVT floor, and it makes landfall in the reanalysis grid cell next to the tide gauge. Again, another asterisk saying, I know this definition is subjective, but I've run the same analysis with other alternative definitions of what nearby is, considering the nearest the nearest two grid cells, allowing a lower floor on the IVT. They all produce the same qualitative result. So again, not very sensitive to that subjective analysis choice. Okay, so I count high tide flood days, count AR days, and finally I count the number of days when both a high tide flood occurs and an atmospheric river passes nearby the gauge within 24 hours of the flood. Call this high tide flooding and atmospheric river days. We'll make this a little bit more concrete. So here's an example of the analysis. So here I'm showing two different water level records, one from San Francisco at the top during 1982, 1983, and on the bottom from Toke Point, which is more north, up in Washington during 1997, 1998. So these are both El Nino years. The blue lines are the hourly water level records at those two locations. the dashed horizontal line is that impact-based threshold. You'll see a blue dot wherever the observed water level overtops that threshold. So these are identifying high tide flooding days. Okay, and for lack of better symbols, I've put these little orange sort of dots at the top. Those identify days when an atmospheric river passed by that tide gauge. So visually, you can start seeing when you have an atmospheric river day, when you have a high tide flood day, and also times when you have an atmospheric river and high tide flood day. So that's really what the analysis looks like. Couple last technical points before I get onto the results. I think this was clever. To interpret the results, I also count one more thing. I count what I call the number of hypothetical high tide flood days that would have occurred from tides and mean sea level alone. Okay, so what I do here is I'm interested in the floods that would have happened regardless of whether there was an atmospheric river. So what I do is I take the hourly water level record, and I'll describe how I do this later. I essentially remove through time series analysis the storm surge bit. So what I'm left over with is mean sea level change plus the tides. And then I count again, how many days did you get still water level above the threshold? And this I call the hypothetical number of high tide flood days. Always important to quantify uncertainty. So we've got some finite records here. So to quantify the sensitivity of my results to the finite record length, I run 1,000 bootstrap iterations on all the statistics here. So if you see any shading, it's the 95% confidence interval quantified through bootstrapping. And I'm also looking to test particular hypotheses. So I want to know whether high tide floods and atmospheric rivers co-occur more often than you'd expect from random chance. So I am forced to formalize this notion of random chance. I'm forced to state formally my null hypothesis. So to do this, I use simulations of synthetic stochastic processes. So for example, I will simulate two random Poisson processes where the occurrence rate of the respective Poisson processes are taken from the data. So I'm essentially simulating this pretend number of high tide flood days and this pretend number of atmospheric river days. The number of occurrences matches what happened in the data, but the timing is totally random. So what I do is I simulate those random series and then I count how often they co-occurred, again, by definition, due to random chance. And then I compare those to what happened in observational reality. And depending on how often the simulations give me more co-occurrences than the observations, that lets me quantify significance in a p-value. So here are the results. So first, just spatial patterns of the occurrences. So I'm showing here the number of high tide flood days on the left and number of atmospheric river days on the right during the study period. Do notice the differences in the color bars. On the bottom, there were at every site more atmospheric river days than high tide flood days. Looking a bit closer, we see some clear large-scale spatial structure. We see a general pattern with latitude such that more high tide flood days and more atmospheric river days happen at northern latitudes towards Oregon and Washington. For example, the fewest high tide flood days occur in Central California around the San Francisco Bay, and the fewest atmospheric river days happen along Southern California. Last sort of geographic anomaly to point out is that Puget Sound is a bit, looks a bit different than we'd expect from latitude alone. There were fewer HTF days and fewer AR days than you'd expect just from the latitudinal trend. This is old hat. This is not a revolutionary new result. We know from past, say, NOAA reports on high tide flooding that we get more high tide floods to the northwest than the southwest, and we know from studies of atmospheric rivers over the past few decades that you tend to have more atmospheric river days experienced to the northwest than the southwest. Okay, so this isn't new. This is kind of a sanity check. What's new here is that I'm going to interrogate what the relationship between these two things is. So here are, okay, so let me try to walk through this because it's a bit tortured. I'm going to compute two things here. I'm going to quantify the percent of flooding days that were also atmospheric river days. That's what's on the left in percentage terms. And I'm also going to quantify the percent of atmospheric river days that were flood days. That's on the right. So let me put this in perspective. The left quantity, the percent of high tide flood days that are atmospheric river days, as this value tends towards 100%, it's telling you that high tide floods are only occurring during atmospheric rivers. That means that the interpretation is that in that case, atmospheric rivers would be a necessary condition for flooding. Okay, the interpretation of the percent of AR days that are HTF days, this is on the right, is slightly different. As this number approaches 100%, it indicates that atmospheric rivers always lead to high tide floods. Okay? In other words, it's showing us to what extent atmospheric rivers are a sufficient condition for flooding. Okay, so that's the interpretation there. Okay, so let's go to the left. Percent of HTF days that are AR days. Depending on where you are along the coast, you could have anywhere between 10% and 63% of flooding events corresponding to AR days. The highest values are occurring right around the San Francisco Bay Area. If we look to the right, the percent of AR days that are HTF days, again, look at the differences in the color scale. Lower numbers on average. This is because this is a reflection of there being just so many more atmospheric river days. Depending on where you are, between 2 and 15% of atmospheric rivers coincide with high tide flooding days. Okay, with the largest value seen along the Oregon and Washington coasts. What does this all mean physically? What these results are suggesting, especially the one on the right here, it suggests that an atmospheric river alone is seldom enough to give you a flood. Presumably, you have to have an atmospheric river coincide with either a high mean sea level, say during an ENSO year, or an anomalously high tide. You have to have the coming together of multiple factors to cause a flood. Again, usually it's not just the atmospheric river alone that can cause it. Something I'm not showing because it would be a very boring plot to show is my null hypothesis. If I was to plot, instead of the observed percentages here, the simulated percentages based on my Poisson processes, and I plotted them on the same color bar, they'd all go to just deep blue. Okay, very few co-occurrences are expected from random chance. So these values, with one exception at one site in Southern California, at 23 out of 24 sites, we find that these observed percentages are much higher than you expect from random chance. So it's suggesting a meaningful relationship between these quantities. So those were spatial patterns of these kind of time averages. Now I'm going to sort of look at a different axis here and look at temporal behavior of averages along the whole coast. So these are all time series of quantities averaged along the entire coastline. Okay, so the solid blue line is the average number of high tide floods each meteorological year. And the orange curve is the number of atmospheric river days per year. We see they both show substantial variability. On any given year, you could have between 1 and 14 high tide floods, again, averaged along the West Coast, and between 7 and 21 atmospheric rivers making landfall. My question here is, do the atmospheric river frequencies explain why you have different number of observed high tide flood days? And the answer, it doesn't matter. In other words, the solid blue and solid orange curves are totally uncorrelated. Okay, that is to say, if you have interannual variability in the number of floods observed, it's not because you had changes in the number of atmospheric river days. The first thing we notice is that the blue, in contrast to the blue versus orange, if we compare blue to black, so black is the average mean sea level along the coast, there's a really strong correlation, about 0.7, very highly statistically significant. So it looks like changes in mean sea level, for example, the high mean sea level seen in 1982, 1983, 1997, 98, both corresponding to El Nino years, that's an important driver of interannual changes in high tide floods. In fact, compare the solid blue, which is the observed high tide flood days, to the dashed blue. This is that hypothetical high tide flood days quantity. This is the floods that would have happened absent any storm surges, only from mean sea level and tides. And we see that the blue dash curve sits below the blue solid curve. That means that if you remove storms, you would get fewer floods on average. However, if we just track the interannual variations of the blue solid and blue dash curve, they track each other really, really well. Correlation is actually 0.9. So this is suggesting that while you would get fewer floods in the absence of storms, the interannual variability is largely determined by changes in mean sea level and the tides. Okay, so that was the relationship between atmospheric rivers and high tide floods. Let's get a little bit more into the physics and look at what's driving storm surge. Okay, so here's again my methods for this next section. Again, the question is what's driving storm surge? So I'm going to quantify storm surge and their causes during atmospheric rivers. Okay, I'm going to follow a composite analysis approach similar to Shinoda et al. So what I do is at every tide gauge, I identify every single atmospheric river that passes by. Okay, and I only take the time when the maximum integrated vapor transport associated with that storm happens. And I say this is the time that the tide gauge felt the strongest effects of the storm. So I take that timestamp and then I take the associated daily storm surge from the tide gauge data, which I calculate from the observations, but by first removing the tidal prediction, removing a seasonal cycle and a trend, and then I high pass filter based on a 20-day moving median operator. Why 20 days? Well, this is similar to previous studies. What we're doing is we're separating high frequency storm behavior from lower frequency mean sea level, and 20 days is a good balance there. You can change this to 10, 15, 30 days. You get pretty similar results, not super sensitive to that particular cutoff. And again, I use the moving median as a robust tool to identify extremes so that I don't sort of have the extreme bleeding into the mean. So it better separates the extremes there. Again, just a figure to demonstrate my methods. Here's the observed daily water level at San Francisco on the top. The middle panel is the same thing, but after I've detided, deseasoned, and detrended it. And then finally, the bottom panel is after high pass filtering. So it's this panel C that is the subject of my study thereafter. Okay, so I compute the equivalent of figure C for all my time series, just to give you a sense of the magnitudes of storm surge. So here's 9 sites. As we go from top left to bottom right, we're going north. Okay, the blue bars are the observed storm surge magnitudes in centimeters during atmospheric rivers for each of these sites. And what we see is as we go from south to north, we find that the distributions are more peaked and smaller in magnitude to being more slumped with possibly higher magnitudes as we go south to north. That is, you're getting more variability and higher magnitudes as you go north. The gray bar, I've sort of identified where that high tide flooding threshold generally is. And consistent with things I said before, we see that the storm surge alone isn't usually enough. Sometimes it is, but it's usually not enough to overtop that threshold. Usually you need, again, that mean sea level and or tidal anomaly to get you there to the flood. So that's what it looks like. Here's the data in a little bit more of a geographic form. So these are the, on the left, the average, and on the right, the standard deviation of the observed storm surges at every site. Even though I use mean and standard deviation, realize, like from the previous slide, these are non-normal distributions. And what we see is, again, consistent with what I just said, you have this large scale spatial structure such that storm surge during atmospheric rivers becomes generally larger in magnitude and more variable as you go to higher latitudes. For example, you have means and standard deviations only on the order of a couple centimeters to the south, where you get a couple decimeters, both in terms of the mean and the standard deviation to the north. Okay, so this is the observed behavior that I'm trying to understand. So to try to understand this, I'm going to build a simple linear regression model. I'm going to assume that this storm surge response, or rather this storm surge behavior, is a linear response to local atmospheric forcing. So I pose this regression model as in equation 1, where zeta on the left-hand side, this is the storm surge. And then I say that this is the linear superposition of these zeta hat terms. So I've got 4 different zeta hats. They all have a subscript, pi, tau, p, and q. Those are related to the different forcing mechanisms. I'm using pi to be the zonal or onshore winds, tau to be the meridional or northward alongshore winds. P is barometric pressure and Q is precipitation. So I form this regression model, and then epsilon is the residual. But also, given the timescales we're interrogating here, I don't necessarily expect that the storm surge response to any variable, even though it's linear and the forcing is local in my assumption, I assume that the ocean response could be transient. That means that it may not be perfectly in phase or an anti-phase. So each of these zeta hat terms, as I'm showing in equation 2, I'm allowing it to be proportional to the forcing x. So I've got some regression coefficient a sub x times the forcing x. But I have this other term, b sub x, h of x, where h is the Hilbert transform, or the quadrature function. So by having each of these zeta hat terms be the sum of both a perfectly in phase or anti-phase and the Hilbert transform, which is orthogonal to that, I'm able to capture arbitrary phase relationships between the forcing and the response. Okay. So I solved this model using ridge regression because I may be dealing with, and I am dealing with, correlated predictors. And what I end up with is what's on the right. So the right shows the modeled averaged and modeled standard deviation in storm surge. So I'm going to toggle back and forth between this slide and the last one. And we can see that it gets the pattern pretty well. It gets qualitatively the increase, the stronger surge and more variable surge as you go to higher latitudes. Here's a different way to look at the same data. So now we're again looking at sites from south to north, going left to right along the x-axis, and this is average mean surge on the axis in centimeters. What's nice about this model is that I can sort of separate out the different contributions of the different forcing mechanisms. So the black is the observed storm surge. The orange is the full model solution for storm surge, so apples to apples comparison. But all the other colors are the other contributions from the winds and pressure and rainfall. Okay, so black and orange track each other pretty well. The model captures most of the structure in the data. The next two most important curves, the next two higher curves, are the green and purple curves. So the green is the ocean's response to barometric pressure. So this is pretty consistently amplitudes of a few centimeters along the coast. Purple is the alongshore wind contribution. This term seems to grow in importance from the south in San Diego, being very close to zero, all the way up to about 10 centimeters at Toke Point outside of the Salish Sea in the Puget Sound. So we have this sort of linear or sort of monotonic almost increase up to Toke Point. Values fall off once you get into the far right sites, which are in the Puget Sound. Okay, so pressure and alongshore wind seem to be most important. The light blue is precipitation. This is certainly less important than alongshore wind and barometric pressure, but at most sites, the contribution is distinguishable from zero. So it suggests that rainfall makes a significant, albeit secondary, contribution to the storm surge response. Finally, the yellow is the onshore wind. This at most sites, this is not distinguishable from zero. So we conclude that onshore wind is not an important driver. This is all for the average storm surge response. This is a plot related to the variability. So now what I'm doing here is I'm quantifying the observed variance explained by the different terms. So again, the orange is how much observed variance in storm surge I'm able to explain by the model. So pretty consistently up around 80% of the variance, which is pretty good, I think. But it becomes more interesting again when you start looking at the other colors, the green, the purple, the blue, and the yellow. Similar to what we saw on the last slide, the green and the purple curves tend to be the highest, explaining those variants. So we see that across all sites, barometric pressure explains between about 40 and 60% of the data variance. Alongshore wind is also important, becomes most important from about Central California all the way up to, again, the mouth of the Puget Sound. But it's less important in the Puget Sound and along Southern California. Again, we see that light blue curve, which represents the rainfall contribution. It is smaller, but it is, again, at most sites distinguishable from zero. And finally, the yellow curve is mostly indistinguishable from zero, meaning that onshore winds don't play as important a role. Now, I'm just going to skip to the results here. So there's a lot of equations. So what's my question? My question is, okay, that linear model, that regression model I just showed seems to work great. We're explaining like 80% of the variance in the data. You get this nice picture of how much, how important alongshore winds are relative to pressure, relative to rainfall, all this stuff. But it's a regression analysis. It's based on just the covariance between time series. It's a fair question to ask whether this is really telling us anything about causation. So to get at this question of correlation versus causation, I asked myself, are the regression coefficients? So remember, if we go back a couple slides, I've got this regression model. I have 8 regression coefficients. I have 4 of these A terms, 1 for each of the forcings, and 4 of these B terms, again, 1 for each of these forcings. My regression model returns values for all those regression coefficients. And I can say, are the values of those regression coefficients consistent with what I expect from first principles? So again, I'm going to, because I think there's only maybe 1 or 2 physical oceanographers in the room, so I'm not going to go into this, but suffice it to say, I sound physical oceanography. And I make these assumptions about space and time scales of variability, what processes are important and not important. If you're really interested in the physics of this, you can go, it's all sitting in the supplementals of the paper. I pose some governing equations. These are just, for those of you who are into this kind of thing, these are just sort of forms of the shallow water equations, how I believe mass conservation and momentum conservation in the alongshore and onshore directions behave. I go through, again, forgive me for doing this, but I skip through and I sort of solve the equation and I derive something like the same form of the regression equation. In other words, I come up with first principles based estimates of what the regression coefficients should be if the physics I'm entertaining is valid. And what really matters is this curve, this plot rather. So what I have here is I have 8 panels, 1 panel for each of those regression coefficients. And what I'm showing are in blue. In blue is the expected range of that coefficient based on the first principle of physics I skipped over. And again, I can go back to it if anyone's really interested in it, but just given that I don't think everyone's a physical oceanographer, I don't want to lose you all in the last few minutes of this. Blue is what you expect from theory. Orange is what you get from the regression analysis. So the lambda value along the bottom is the ridge regression coefficient. Okay, the vertical dashed line at 0.3 is the value I select. And what I'm trying to show here is that once you have lambda values bigger than 0.3, you pretty much converge to a stable solution or an acceptable solution with the ridge regression. But it's the 0.3 value that I use in the paper. Really, the point here is that the blue shading and the orange shading, in all cases, pretty well overlaps. That is to say, the regression coefficients I obtain from the observations are, in fact, consistent with basic considerations from very simplified physical considerations. So this provides support, kind of a glorified back of the envelope kind of calculation, provides support that what I'm seeing with the correlation-based regression analysis is indeed telling me something about causal reality. Okay, so I'll end with a couple summary points. So here are my key points again. Again, high tide floods on the West Coast co-occur with atmospheric rivers more often than you expect from chance. Between 10 to 63% of floods co-occur with atmospheric rivers. In terms of understanding the physics of the storm surge, it's alongshore winds and barometric pressure that are really the primary drivers. Okay, but interestingly, we hypothesize that rainfall can also have a secondary effect. Again, encourage you, if you're really interested in it, to go check out the manuscript. Again, it was published a couple months ago in GRL. And I'll end with a couple next steps and future work. This is really a first pass at the topic. I showed you, for example, spatial maps of just time integrated quantities, and I showed you time series of spatially averaged quantities in that first section. It still remains to be determined whether, I really like to dig down at, look at the year-to-year variability at particular tide gauges. That was sort of precluded just due to the space constraints of the journal, but there's still room for a more thorough study of the spatio-temporal statistics. Second point, I looked at the West Coast, but atmospheric rivers make landfall elsewhere along the eastern boundaries of ocean basins. So it would be interesting to see what happens in other regions, whether what I'm finding here on the US West Coast also applies to places like Northwestern Europe or the South American coast, other regions that we know experience these events. Always good to more thoroughly quantify uncertainty. These results were based on that Scripps atmospheric river catalog. There are dozens of other atmospheric river catalogs. At the encouragement of one reviewer, we did undertake a sort of a first cut uncertainty quantification, rerunning our basic statistics using all of the AR catalogs in the ArtMIP projects. This is about 24 or so that we used. Uncertainties are important. They don't qualitatively change the story here, but there are important uncertainties which I think need to be understood more. And in particular, trying to identify which atmospheric river catalogs are really most helpful and informative for coastal impact studies. Speaking of impacts, so I considered high tide floods, but you could imagine other types of impacts of atmospheric rivers like waves and erosion. That would be good to study those. I use the NOAA flood stages, which are really a parameterization. It's an extrapolation based on a few locations with known flood stages to all tide gauges. But it would be informative to quantify how sensitive our results are to alternative definitions of flood stages or stronger floods, for example, moderate or major floods. Again, the extent of the physics here was really just a regression analysis. It would be really, really helpful, especially for, say, testing that hypothesis that precipitation drives the dynamic response, to use a high resolution model. And finally, of course, it would be interesting to sort of inquire in a bit more depth how all of these considerations play into what we already know about the future impacts at the coast anticipated from sea level rise. Do they aggravate those type of effects? So that's the study. Happy to take any questions. Thanks very much for your time.
Thanks very much, Chris. That was a fascinating and really beautiful talk. Do we have any questions from anyone?
No one asks a question, I'll just bore you with those equations and go back to them.
It's unusually quiet today.
Okay.
Give it a moment, see if someone. Oh, Roger, are you about to ask a question?
Yeah, the telltale turn on the camera move. Very cool research, Chris. This is just a very basic question, but why is the Central California coast behaving out of latitudinal gradient? I think it was in not the atmospheric rivers, but the high tide flooding. What I mean, that's not the just like background.
Yeah, sure. So there's actually a couple of ways in which the San Francisco Bay Area is unique. The one that jumps out the most, and maybe the one that provoked your question, was I was showing this plot of the percent of flooding days that were also atmospheric river days, and the Bay Area just popped out. You know, it was something like in that area, something like 50 to 60% of all the floods coincided with atmospheric rivers. That result, so it seems very interesting from that perspective. So why in the Bay Area are floods so often tied to atmospheric rivers? Well, part of the reason is you can explain this in a sort of statistical sense that whereas you have almost a monotonic gradient in the atmospheric river days, that is, as you go from south to north, from San Diego to Puget Sound, you almost monotonically increase due to the orientation of the storm track how many atmospheric rivers you get. So you can imagine this sort of linear ramp up in AR days as you go from north to south. The spatial structure of the flooding days isn't so monotonic. You actually get a minimum in the flooding days around the San Francisco Bay Area. So you don't see this sort of latitudinal trend. You see sort of a minimum around the Bay Area. So it's a region where whereas you have this linear increase in AR days, you have, as you go south to north, you have a decrease and then an increase in the number of high tide flooding days. So just from those functional forms, sort of do the math and you expect there to be a maximum in the high tide flood days that are AR days just from that. But that's just a statistical explanation. Why are there so few floods? The real question is, why are there so few flooding days in the Bay Area? That I'm not sure. You know, we know that the tides and mean sea level are really important sort of ingredients to this. And it may be, for example, that, again, I'm not really an expert in the tides in this region, but it could be tidal behavior that is distinct along, say, Southern California, the Bay. Yeah, I don't know. I have a couple of hypotheses, mainly related to the tides, but I'm not sure. One caution, though, is that, as I said earlier, we're using NOAA's standard high tide flooding threshold parameterization. That floods occur when you're about 56 to 64 centimeters above high tide. There are a few locations where that parameterization doesn't work well. And actually, the San Francisco Bay is one of them. If you look at empirical, sort of local, thresholds, flood stages that, NWS folks in the field have identified, it's actually a bit lower in San Francisco. You only need to get about 40 centimeters or so above mean high or high water to affect a flood in that region. So that's one of the results that may be a little bit unrepresentative because I'm using this sort of more uniform, right? There are pros and cons to the NOAA framework. One is that you have this uniform framework for the entire coast. The trade-off you make is that you may not be representing impacts quite so well at individual locations. So before I dig too much into understanding why the Bay Area pops out, it would be good to sort of quantify the sensitivity to what we're defining as a flood in that region. So, but yeah, anyway, that's all a way of saying I don't know. I can explain it through just the geographic patterns. I don't know the processes underlying it, but certainly since those regions really pop out, to be explored more. So there are a couple questions that came in the chat. Do you want to read those, Craig, or should I just?
No, I was going to ask, it's just nice to break up some of the chatting. So I was hoping to ask Vivian if she would like to unmute and ask a question herself, if that's okay.
Right. I was just curious to know, I mean, you looked into atmospheric rivers and storm surge impacts, but what about the flooding also relating to the heavy rainfall that would occur during those events?
Do you mean coastally or inland?
Well, preferably the heavy rainfall also near the coast.
Yeah, well, there's a couple couple answers to that question. Some of those considerations are already folded in. So what I've done is when I identify when these two things co-occur, I've been a little bit agnostic in terms of what the driver is, and I actually allow for a rainfall contribution. Insofar as the reanalysis meaningfully represents the rainfall process, that's folded into my regression analysis, for example. So I am arguing, actually hypothesizing, that the rainfall is playing a secondary role in generating the coastal storm surge. Okay, so which is a kind of a neat result. But there's a lot more you could imagine to probe into this too. I mean, again, so I'm looking at precipitation from a reanalysis. You can imagine a couple things that, you can imagine maybe it's more relevant to look at stream flow. I mean, you can consider the following scenario where you say you have an atmospheric river make landfall. You've got these strong winds and low pressures, and that's driving this immediate storm surge. But then that filament, that atmospheric river, is sort of then traveling over land. It's raining out all this precipitation, this extreme rainfall over land, and that's being sort of collected over the watershed. And that takes a finite amount of time to make its way into the rivers and subsequently back into, say, an estuarine system like the San Francisco Bay. What does that increased discharge at some later time do in terms of storm surge? Maybe you expect that there's this kind of secondary surge sometime after the landfalling time related to this increased stream flow from the collected water, the rainfall over the watershed. I haven't looked into that. That would be a really fun problem to tackle. You can imagine looking at river gauge data of stream flow to see if that's what's going, if that you actually see evidence of that. But yeah, I'm particularly interested in this question. I think the question of freshwater input as a forcing on storm surge is one that hasn't been studied super well. And I'm very interested to see, one, if it's important to understanding these flooding events the way that we're defining them here, high tide floods, but also physically, how we understand the nature of the ocean response to freshwater input at a localized source like a river mouth. Does that get at your question? It's kind of circuitous.
Yes, that was a good response.
Great question.
Thanks, Vivian. That was really interesting. Alan, would you like to unmute?
Sure. So I found this AR business pretty fascinating. So my first thought was, can you look at a forecasted AR and figure out, will you have a high tide flooding event?
Mm-hmm.
And maybe that would give you a leg up on what's going to happen in the next few days.
Yeah, no, I think it's funny. I've given this talk a couple times now, and there's never fails that someone asks that question. So I take it to be, that's an important question. Yeah, I mean, as the couple people in the room who are familiar with me know, that I'll probably appeal to doing the simplest thing. So I have, great respect for, but also no interest in sort of running very complicated forecasting models. Immeasurable value in that's not my skill set. What I can imagine doing is sort of doing the, again, back of the envelope sort of complementary exercise. You could imagine something very, very simple along the lines of what you're suggesting. Remember back to that time series plot or the histograms I showed. What I said was that the storm surge associated with an atmospheric river by itself is usually not enough to give you a flood. You need to have that on top of either an anomalous tide or a higher mean sea level. A mean sea level anomaly that persists for months at a time, or at least weeks at a time. So you can imagine something really, really simple. You could say, okay, I don't have a good sense of the lead times of these predictions, but say we knew 3 days in advance that an atmospheric river was gonna hit with confidence. Mm-hmm. You could say, okay, let me just pretend that. So I've got to add 3 things: surge plus mean sea level plus tides. I say, okay, mean sea level is what it is right now at the tide gauge. So that's piece 1. Tidal predictions are pretty good. So I've got my tidal prediction. And so I know that the base level on which any storm surge will act, okay? So the sort of increase in freeboard. And then I could imagine just doing some simple statistical exercise where I take those sort of empirical histograms of the storm surge, which I showed in one of my earlier slides for those 9 sites. Just imagine doing sort of this Monte Carlo exercise of just repeatedly, drawing from that distribution, adding it to the maximum predicted tide plus mean sea level, and see what are the odds of a flood. It could be that maybe you luck out in that you're at a time of year where the tides are lower or mean sea level is lower. And even if you entertain the biggest type of storm surge associated with one of these storms, you're safe because mean sea level is lower, or vice versa. Maybe you have conditions that are really ripe for it. It would be an exercise that could take you, if you had the code set up, could take you 5 seconds to run. and you'd have some probabilistic sense. Again, it would be extremely simplistic, very crude, but I think it would be sort of a meaningful sort of first order type of calculation. That's what I could imagine that one could do trivially based on the results here. But of course, yeah, you wouldn't want to make some sort of decision based on that kind of calculation alone, but it could give you a sort of a ballpark estimate.
Thank you.
Yeah, thanks for the question. Oh, you're muted, Craig.
Yeah, really sorry. So thanks, Alan. That was really interesting. I noticed Roger made might be interested in adding another question just before we. I know we're about noon here, so we should probably close off soon. But if anybody has any final questions or comments, please speak now.
I'd also say thank you very much to Klaus for the links to the study. I appreciate that.
Silence, very quiet. Oh, did Klaus put some links in the?
Oh yeah,
chat?
he and I were chatting about an author in California writing about these things, and he sent me the link to the paper. So, well, thanks everybody.
Thanks everyone for joining us. Thanks ever so much again, Chris. It was fascinating to talk. I really look forward to uploading this one. Sorry again for my technical issues this morning. I look forward to looking back to it in a less stressful state.
There you go.
Cup of tea later.
No
Yeah,
worries.
It was an excellent talk. It was really beautiful as well.
Thanks.
Thank
All
you.
right, everyone have a good day. Bye.
Cheers.